In this video, we're going to talk about how to use the half reaction method to balance redox equations. So the reason that we like the half reaction method is because this method makes it very clear how many electrons are being lost in the oxidation half of the reaction and how many electrons are being gained in the reduction half of the reaction. And that number of electrons is extremely important for the electrochemistry calculations that we'll be doing in the next set of notes. So the simplest equations to balance are the ones in acid, in which case what you do is you assign oxidation states to all of your species, and that way you can identify which species are oxidized and which species are reduced and split your reaction into two starting half reactions. Then balance each half reaction using water to adjust the number of oxygens and protons, solvated protons, to adjust the number of hydrogens. And then finally balance charge using electrons. And you can usually verify that the number of electrons you're using makes sense by looking at how the oxidation states changed for the species in that half reaction. We then take our two half reactions and combine them to make an overall reaction. When we do that, we have to make sure that the electrons fully cancel. And so in all likelihood, you're going to have to multiply one or both half reactions by some coefficient to bring the number of electrons produced in the oxidation half reaction equal to the number of electrons gained in the reduction half reaction. If you're going to balance a reaction equation in base, we think that the easiest way to do that is actually to balance it in acid first and then add sufficient hydroxide to both sides of the equation to completely cancel out the solvated protons, making sure, of course, that you're adding the same amount of hydroxide to both sides of the equation. If you are dealing with a redox reaction that happens under neutral conditions, then it's okay to produce acid, but there won't be significant amounts of H+ solvated protons floating around in neutral water that you would be able to use it as a reactant. The concentration of solvated protons in neutral water is approximately 10 to the minus 7 moles per liter. And similarly, the concentration of hydroxide in neutral water is also around about 10 to the minus 7 moles per liter. And so those aren't going to be abundant enough to use as reactants, but it's perfectly fine if either of them are generated as products. So let's start off by looking at an example in acid. In this case, we're looking at the reaction of sodium dichromate, and we know that all sodium salts are soluble in water. So this works out to 2 sodium cations and then a dichromate ion, which must therefore have a charge of -2. And it's reacting with potassium bromide, which will correspond to potassium cations and bromide anions in aqueous acid. And we're going to get molecular bromine and a chromium +3 cation. So recognizing that the sodium and potassium ions are just going to be spectator ions, if I write out my preliminary reaction, that means that I'm expecting to see sodium dichromate, or just dichromate, reacting with bromide in the presence of acid, which I'm putting over the arrow just to remind myself that I'm allowed to use acid and water when I'm balancing later, to make bromine, which should be dissolved in water in this case, and the chromium +3 cation. So I start off by assigning oxidation states. 2 of my ions are monoatomic, so that makes it very easy. The oxidation state is the charge, and so the bromide has an oxidation state of -1, and the chromium +3 has an oxidation state of +3. My molecular bromine is a neutral molecule with only one element in it. The 2 bromine atoms in that bromine-bromine bond are going to split the electrons evenly, and therefore the 2 bromine atoms are both going to have an oxidation state of 0. In the case of the dichromate ion, this is where your high school rules are going to work just fine because oxygen is significantly more electronegative than chromium is. And so in any chromium-oxygen bond, the oxygen is going to get the electrons. bringing it to a total of 8 valence electrons in this oxidation state counting system, and an oxidation state of -2. So we have 7 of those at -2, which is -14. And we want our total oxidation states to add up to -2. And that means we're going to need the 2 chromium atoms to have the same oxidation state, which I'm just reporting here as X. And in order to make this equation work out, for 2x minus 14 to be equal to -2, X has to be equal to +6. So the chromium atom is going to have an oxidation state of +6. So to determine which species are involved in which half reaction, I look at those oxidation states. I can see that the chromium and dichromate had an oxidation state of +6, and that has been reduced to +3 in the chromium product. So the chromium is the species involved in the reduction half reaction. So I will start setting that up by saying that the dichromate ion is going to be producing a chromium +3 cation. And the other element which changes oxidation state is bromine. We can see that the bromide ion has lost electrons, become less negative, going from having an oxidation state of -1 to an oxidation state of 0. So my other half reaction is going to be my oxidation half reaction, in which the bromide ion goes to molecular bromine. I can balance those in either order, doesn't matter. I'm going to start with the bromine one because it looks easier. I start off by balancing all my atoms that aren't oxygen or hydrogen, so bromine it is. I need 2 bromide ions in order to produce the bromine molecule containing 2 bromine atoms. Now all of my atoms are balanced. I just have to balance my charge, and to do that I add 2 electrons on the product side. This is a loss of electrons. I expected to see the electrons on the product side. For the reduction half reaction, start off by balancing everything that is not oxygen or hydrogen, so fix my chromiums. I need 2 chromium +3 cations. Then I balance my oxygen atoms by adding water. In this case, I need 7 water molecules to balance the oxygens. Balance my hydrogen atoms by adding H+, and I now need 14 solvated protons in order to balance out those hydrogen atoms. And then finally, I need to add electrons to balance the charge. So right now, the total charge on the reactant side is +12. 14 plus 1s plus a -2 is +12. The total charge on the product side is +6 because I have 2 +3s, and that's +6. So to get from +12 to +6, I need to add 6 electrons to the reaction side of this reduction half reaction. And again, since reduction is a gain of electrons, I'm happy to see that the electrons went on the reactant side. The last thing I need to do is I need to combine those 2 half reactions to make the overall reaction. And to do that, I need to make sure that the electrons cancel out. Since I have consumed 6 electrons in my reduction half reaction, that means that my oxidation half reaction has to make 6 electrons. So effectively, I need to multiply my oxidation half reaction by 3, or do it 3 times, in order to make enough electrons for the reduction half reaction to consume. If you can add this up looking at it like this, that's fine. Otherwise, what you can do is you can go through and adjust the coefficients on everything in the oxidation half reaction, multiply them all by 3, which would mean we would then have 6 bromide ions, 3 bromine molecules, and 6 electrons. The 6 electrons from each half reaction will cancel, and we can add everything else up. So that's going to give us a dichromate ion reacting with 14 solvated protons and 6 bromide ions to give 2 chromium 3 cations, 7 water molecules, and 3 bromine molecules. And if you were to go through and check, you have the same number of atoms of each element on both sides of the equation, and you have the same total charge on each side of the equation. And both of those have to be true for the overall equation to be balanced.